In this problem, we are given the live load for the bridge truss shown, which consists of a uniformly distributed live load of 30 kN per meter of truss and a concentrated load of 90 kN. Using influence line diagram, we are tasked to calculate the maximum force of member CH. And to solve this problem, using influence line diagram, we began placing a 1 unit load that would cross over the entire span of the beam that has a magnitude of 1 unit. And the distance from the support at A, we call this distance x between A and the 1 unit load. And to solve for the reaction at the support, let's call this R sub A. And this one at the roll support, let's call this R sub F. The value of the reaction is dependent upon the placement of this 1 unit load across the entire span. So by taking summation moment at point A, we can solve for RF. So we have the 1 unit load that would induce a clockwise moment, so it's negative, times its moment arm distance of x, and plus R sub F that would induce a clockwise moment, so it's positive, times its moment arm distance of 5 times 4.5 meters, that is equal to 22.5 meters, all equal to 0. So rearranging this equation, we can get RF that is just equal to x over 22.5. And to solve for the reaction at A, we'll basically take summation force vertical equal to 0. So we have R sub A plus R sub F that is equal to x over 22.5 minus the 1 unit load, all equal to 0. Rearranging this equation, we get RA that is just equal to 1 minus x over 22.5. Now once we have our reaction, we can begin solving for the influence line diagram and compute the maximum force of member CH. And to do this, we apply method of sections to solve for the reaction. I mean force member CH by exposing the tensile force of the bar members HI, assuming tension. We have CH and BC. So let's consider the left section of the truss. So these are the tensile forces we have exposed. These are BC, CH, and IH. And to solve for the first member on CH, assuming the 1 unit load is between A and B, that is where the value of x is between 0 and 4.5 meters. So taking summation force vertical equal to 0, we have R sub A that is equal to 1 minus x over 22.5 minus the 1 unit load plus the vertical component of CH that is going downward. So this is negative because it's going downward. And to get the vertical component of CH, we multiply this by sine of theta, which is this angle right here. And to solve this angle, we utilize the arctangent function, tangent theta equal to the opposite side of 3.6 meters divided by the adjacent side of this right triangle. That is a value equal to 4.5 divided by 2. So solving for angle theta, this is arctangent of 3.6 over 4.5 divided by 2, that is equal to 58 degrees. This is equal to this angle here, and as well as this angle, and so on. So sine of theta, that is sine of 58 degrees, all equal to 0. Simplifying this expression, we have 1 minus 1, that's 0. Solving for CH, that is just equal to negative x over 22.5 sine of 58 degrees. Next, we begin solving for force member CH, where the load crosses beyond point C. So let's place the 1 unit load beyond point C. That is a distance from A to the 1 unit load. Let's call this X. And we now begin considering the interval where X is between 9 meters, that is at point C, and at point F, that is where X is equals 22.5 meters. So considering the left side of the section where we got the truss, and by taking summation force vertical equal to 0, considering the left section, we now have R sub A, that is 1 minus X over 22.5 minus the force member CH and its vertical component, that's sine of 58 degrees, all equal to 0. Solving for CH, we have 1 minus X over 22.5 all over sine of 58 degrees. And for the next step, we begin plotting the points in our influence line diagram, the force experienced by CH. So using this equation to plot the point between 0 to 4.5 of CH, we have negative X over 22.5 sine of 58 degrees, and at X is equals 0, CH is equal to 0. That is this point right here. Now at X equals, this is 22.5. Now at X equals 4.5, the value of CH is negative 0.2358, which is this point right here. And then we begin considering the force experienced by CH between 9 and 22.5, so we'll use this formula. At X equals 9, the value for CH is equal to 0.7075. And at X equals 9 plus 4.5, that is at point D, the value for CH is equal to 0.4717. And at point E, where X equals 9 plus 4.5 times 2, the value for CH is equals 0.2358. And at X equals 22.5, the value for CH is equals 0. So this is our influence line diagram. And for the next step, we need to solve for this value of X of this right triangle, as well as this value, which we will need to solve the maximum force of member CH. So by taking raising proportion of the triangles, we have X over 0.2358 equals to this base here, that is a length of 4.5 minus X over 0.7075. We get X that is equal to 1.1249. And this value here is equal to 4.5 minus X, that is equal to 3.375. 1. Now to compute for the maximum force of member CH, we begin placing the concentrated load of 90 kN to the point where the value of CH is maximum. That is at this point here, at point C. And for our uniform load, we will place this between the point where we will maximize the area of this triangle. That is between this point here to point F. Now to solve for the maximum force of member CH, we multiply the concentrated load of 90 kN to this value here of 0.7075 plus the uniform load of 30 kN per meter times the area of this triangle. That is an area of 1/2 times the base of 3.3751 plus 3 times 4.5 multiplied by a height of 0.7075. Solving, we get a value of 242.76 in kilonewtons. And since this value here is positive, therefore CH is experiencing a tensile force. And this is our final answer for this problem.